Brother, brother, please give me the ability to walk, brother. Brother, I crave locomotion. Please, brother.
Welcome back, or if you're just joining me now, welcome. This is the second part in a series where I design and build an analog beam robot completely from scratch. So I have talked about beam robots before on this channel a lot, but a quick recap of what they are. Beam robots were an analog robot type that was very popular in the 80s and 90s. They used a series of electronic neurons as their control system or brains that was usually built with a series of voltage sensitive triggers with analog inputs on them. And you were able to get very complex behavior from them. You can see the whole video about beam robots up here. In the last video, I built this robot here, except at this point, it's not really a robot. It's just a series of aluminum channel, lovingly crafted brass wire, and some gear motors. We need some sort of control system, a brain. And to make that, we have to understand some of the basics of what makes beam robots tick. So grab yourself some wine, sit down, and we'll dive into the complex ins and outs of what makes beam robots think, or at least pretend to think. Let's look at the most important part for a lot of beam brains or circuitry, and that is the Schmitt trigger inverter logic gate. On a standard buffer gate, it'll just take the input and determine if it's high or low and then switch the output to do that. It doesn't care where in that the output is. If the trigger point is 2 volts and it's 2.01 volts, it'll be high. If it's 0.95, it'll be low. Schmitt triggers are a little bit different than this. So they actually have two separate trigger voltages, a high and a low, and they basically stay locked into one of those depending on which it was originally triggered in. So we can imagine here that this is the input signal of a Schmitt trigger here. At this point it comes in, this is where it starts, and this is below its second switching voltage. So the switching voltage will be here, it'll be low. The output is low. And as that signal goes high, it goes over top that switching voltage, but it stays low all the way until the second switching voltage here, at which point the output goes high. And then that only stays above that switching point for a little bit and then starts to go down again, but it stays high all the way until it gets down to this point. Switches again, and then that stays low all the way until it gets up to here. Now this means that it basically ignores signals from the middle point of its input. This takes noisy signals and basically filters it to just a high or a low and ignores any of that intermediate noise. So there's basically two main types of beam neurons. They use the same parts, just arranged slightly differently. This arrangement here is called the NV neuron, and this is the NU neuron. Now, I think those are NV and NU, but I have a feeling like maybe it's some sort of Greek letter or something like that. If I'm saying it wrong, let me know in the comments. So this is a Schmitt trigger inverter with a capacitor on the input gate, and then that input is grounded. So when a signal comes in that's high, it will basically push through a high signal to this point. These input gates they don't sink or source any current. So if this was just normal, you would just get a high input and a low output. But because we have this resistor here, this will slowly drain that current out. And so what you'll get is you'll get a pulse that goes high, and then it'll slowly drain down here. And now if we remember, when it gets to about this 2/3 point, the output will switch, and then when it gets to this 1/3 point, it will switch back the other way. It means that we can take a signal input in and then get a delayed signal out that stays on for a certain amount of time that we can determine by the component selection here. However, there's another type of gate here, which is this one here, the NU gate. So this uses the same parts, but they're kind of switched around. So we have a resistor here and then a capacitor here between ground and the input. So when a signal comes in, it's going to go through this resistor. This is basically a direct path to ground. So you're going to get a small signal in here. It's just going to go right to ground until this kind of fills up, in which case that signal will slowly rise here. And we can imagine this comes in. So it's high, we get this, and then as that starts to fill up, it comes up and then levels off here. Interesting part about this, depending on the size of this resistor, is if we make this input go low again, this will actually stay high for a little bit here because it has to discharge back through that resistor as well. So you get a tail off that looks something like that. So this means that we have a way to delay a signal in two different ways. We can have one that goes on instantly and stays on for a bit, and one that has a delay before it goes on and then stays on for a while. The useful part about this is now we can kind of put these together and we can make any arbitrary sequence we want. So with that theory out of the way, let's move over to the breadboard and let's build a couple of these circuits in real life and see how they function in the real world. Here is a simple single NV neuron built up on this breadboard here. This uses a 74HC14, so a 6 Schmidt trigger inverter chip. And I have one of those repurposed as just a up-down, so I can have that toggle high or low, and then that's coupled into the input of this one here through a capacitor, and then that's grounded through a 1.5, I think, mega ohm resistor. So you can see when I push this, the LED lights for a second and then goes out. So that is the delay. So it goes high and then turns off after a set amount of time. Again, if I make this capacitor bigger or this resistor larger, that'll stay on for a longer time. Here I can switch it out for 10 mega ohm. And the light stays on for a much longer time. So then we can use that and couple together a couple different ones of these and build a signal which will propagate down the train. And here you can see as the first LED goes off, the next one goes on. And we can connect these together as many as we want, right? And actually, if we connect the output of one into the input of the next, now we have a system which will flip back and forth forever. We can use that to drive a motor back and forth or any sort of system we want that needs a periodic repeating of some sort of action. And again, we can vary the resistor and capacitor values so we can change how this is going to be biased, left or right, front, back, whatever. Now, if you're an audio person, you might look at this circuit here and think one of two things. First, could I improve that with some gold-plated cables? And yeah, actually, if you go on the link in my bio, you can buy them, only $700. The second thing you might look at is that this looks a lot like audio filtering circuits, so high-low pass circuits. And that is kind of what we're doing here. So we're taking something like this is effectively a high-pass circuit. So it takes a pulse in and stays high for a while, but if that pulse doesn't change, it'll time out and then it'll go back to its original state. And you can kind of imagine like this is filtering out slower frequency signals, but we're talking about instead of like, hundreds or thousands of hertz, we're talking about like 5 or something like that hertz. 3-motor walkers never appeared to be super common in beam robotics. There's a couple designs out there, but I was only able to find a couple circuits or a couple complete circuits for robots. So I ended up designing my own based on a couple previous designs and then tweaking them in ways that would allow me to have a more flexible system. So let's jump over and look at the complete circuit here. So this is what I came up with for my design here. So we have a main loop which uses 4 neurons staggering the main front and rear motors. And those have the outputs of every second one connected to each motor. So you can see this output is connected to this motor and is this output, so it's staggered. So the behavior of this will be that one motor spins one way, the other motor spins the opposite way. So we'll go anti-clockwise, clockwise, clockwise, anti-clockwise, which should allow me to sequence the steps of my motor. So this little circuit here is actually called a microcore and was used pretty extensively in different beam, usually 2-motor walking robots. But because I'm using this in 3 motors, I need a way to control my other motor here, so my waste motor. Now, there's a couple different ways I could have gone about this. You can actually just couple that in between your front motor as well, so those are going to be running at the same time. That isn't really going to give me the behavior I wanted, because I wanted the option to control that front motor, or the waste motor, slightly independently, so influenced off of the main front motor, but I wanted to be able to turn it on for less time when I wanted. So that's why I have a branching section coming off of here, and then 2 extra neurons. So this is actually coming off of the rear motor effectively. But that means I can make these resistors slightly smaller than the other resistors for my other front motor. So this will make less of a vertical step, but more of a forward one. So it allows me to fine tune the leg control a bit more than I otherwise would. And that also gives me the option of changing this. So I could say, have an option to add a larger resistor or change those resistor values, so then I can change the step or the height it's stepping a little bit more. Maybe if it encounters an obstacle, it tries to walk over that instead of just backing away and reversing. Now you might notice there's an extra couple components here, and that's these diodes here. Now what that is for is to control the signal going through our neurons here. So these neurons are always going to be the opposite state of the one next to them. But with 4 here, or more than 4, you can end up with a state where every second neuron is high. So this will be high, this will be high, this will be low. That's useful for some situations, but we want a single signal propagating through one at a time and the other ones to all be low, because we want our motors to be sequencing. So it goes one at a time instead of both motors trying to walk at the same time, which won't work. I mean, you might be able to design a robot that does that, but it won't be easy. So this basically connects every third neuron. So instead of each directly connected, it's every third neuron is connected to the one in front of it, which cancels out the signal from that one, which means that this is always going to have a single signal coming through that, and it won't allow multiple signals to propagate. Now on startup, that means these ones could be high or low, and that will cause some issues, but that'll sort itself out very quickly as the signal propagates through the entire network. There's a couple other things here that I don't have pictured as well. So these motors are not directly driven off these inverters. They have their own motor driver circuitry. I also put a small filtering cap here, which help with stability during times when multiple motors were switching at the same time. Because both my front motors are going to turn on at the same time, it can be a lot of current draw, which causes some issues. Now you might look at this whole circuit and think, Elliot, couldn't you have just connected an Arduino to a couple motor controllers and gotten the same thing? What are you, the microcontroller police? But actually, you could do that, and you would get a robot that functions similar to this. But there is one big benefit that beam circuits have, and it showed out in kind of the superpower abilities of some of the early beam robots, and that is motor feedback. So each of these input gates is an analog signal. So when this is coming in here, this is going to go up like that, decay down, and then turn off. And this is determined by the supply voltage of the previous inverter, as well as the supply voltage of the entire circuit. So when the motors are switching and changing and being loaded or unloaded, that will change the supply voltage of the whole circuit, and especially the chips here, which will mean that these drop faster or slower. So you can imagine the noise of a motor is going to be, that's the kind of midpoint of the voltage, and it'll just be a random up and down signal floating around that point. And when this is loaded, that's going to become much bigger. And if it's stalled, it's going to drop the voltage right down, which will cause these to switch a lot faster. This is kind of a feedback system for the circuit, and it can allow a robot to have a very flexible, dynamic stepping system without adding any circuitry to control that. So when these are loaded, especially near the ends of those travel, when this is getting near the ends of these switching points, our robot's step will be modified, and that can help it get out of some really complex situations with basically no extra control circuitry. And this is kind of the big superpower of being robots. Now that I had a design to work with, I can actually build this in real life and integrate it into my robot. So there was a couple interesting design choices I made here. Well, I think they're quite interesting. But I actually had some pretty big challenges as well with this. My motors, the original 90-degree N20 motors, did not work. They just didn't have the torque needed, so I ended up having to buy some different ones. Thank you, Lean Motor Company from Shenzhen, China. Not sponsored, by the way. I ended up buying some new higher torque versions. Also didn't work. I mean, they did work, but the movement of the robot was so slow that it ended up not doing it. So I actually ended up digging up some standard N20 straight motors that I had sitting around from another project that ended up working really well. This changed the look of my robot a lot, which I wasn't so fond of, and I think I'll have to redesign the legs down the road. But these worked really well from a torque and power perspective, so I think I will be sticking with those motors. The actual control system I ended up building was exactly the same as what I had drawn out, except for obviously I needed a motor driver. So the little output of those inverters is not nearly enough to drive a motor. Traditional beam robots used repurposed buffer or inverter chips to do this often. And I actually originally designed and built an entire system for that, but it turned out to be a little bit underpowered, and now you can just get really good motor driver ICs. So I ended up building a motor driving circuit for that. And for the actual brains on this, I ended up doing a kind of combination freeform and breadboard build. Now, why did I do this? Well, I kind of like both of those. They both have their pluses. I love freeform electronics, but I wanted to mount a couple things, especially my resistor plugs here, so I could adjust the timing of the robot very easily, which ended up to be a little bit easier to do on the breadboard. So after all that, let's have a look at the robot actually working. Well, there we go. We've gone from a collection of AliExpress parts to an actual functional robot. It can actually move, I can adjust the gate, it's got so much more animation now. But it still does have a couple problems. It has no way to know if it's bumping into something. It has really basic feedback built into it. So it can only really walk in a straight line. So our next step in the next video is going to be adding some sensors and feedback to our robot. So if it knows it bumps into something, maybe we can have it reverse or even turn. So stick around for that one. Thanks a lot for watching this video. I'll see you next time. Take care.